is a real snapshot of the universe. The most detailed picture of space humans have ever taken. The cosmic panorama before you stretches for billions of miles. It contains millions and millions of galaxies. And it's the crucible of matter that created you and me. The space is filled with mysteries and wonder. Over the next 5 days, we will blast off on an epic voyage that will take us back to the beginning of space and time. This is the most exciting time to be exploring space. We've got many, many telescopes mapping the heavens. We've sent probes deep into space. We've got robots and rovers mapping planetary surfaces, orbiting bodies out there. We can even, in the comfort of our own home, search for alien life using our desktop PCs. I want to share with you how thrilling space and time travel can be. We'll be sucked into monstrous black holes which can eat whole stars for breakfast. We'll fly through the violent storms that boil on the surface of our sun. I'll challenge you to launch missions into space and join me on a journey to the center of the Earth, hunting for missing parts of the universe. We'll discover the extreme training you have to go through to become an astronaut, and explore how humans will visit and eventually colonize other planets. And in a special show, live tomorrow at 12, we'll probe the mysteries of the red planet, Mars. My chief interest in space comes from study of meteorites. I work at the Natural History Museum in South Kensington in London, where I look after the largest collection of meteorites in Europe. Meteorites are chunks of asteroids that fall from space to the Earth, and we can study them to help learn about how the solar system formed and how everything got going. Some of the bits that I study are very special indeed. This is a fragment of the red planet, but if you want to know more about that, you'll have to join us again tomorrow. Now, space is big. Space is very, very big. Space actually is huge. But where did it all come from? Where did everything in it come from? What made it? What made the universe? Was there anything there before the universe got going? Really, before we touch down on any planets, we need to explore some of the universe's bigger questions. So what we're going to do in our spaceship here together, we're going to travel to the edge of space, which is only about 137 billion miles away, and we're going to see if we can find out what happened then. What did happen? I don't know. Nobody really knows. It's actually described as a big bang, but we don't know what went bang. We don't know why it went bang or what made it go bang, but it was very, very violent, like some of the experiments that I'm going to do in these lectures. And this is why every time this sign flashes up, you must put your safety specs
Warning,
on.
effect imminent. Warning, effect imminent.
Now might be a good time to practice, and you should put your earplugs in. Because the universe and everything in it was born out of an enormous, big bang. with me that that was a fairly big bang? Yeah, but unfortunately, the Big Bang that started the universe was probably absolutely nothing like that at all. The reason is that to hear that noise, you need atoms and molecules. You need an atmosphere to hear things. As they say in the Hollywood movies, in space, no one can hear you scream. So the Big Bang actually was silent. We think, whoops, come here. We think it was probably something a little more like this. Whoa, now that was nice and bright. But the Big Bang, of course, would have been a zillion times brighter than that, because all the matter and everything that made the universe was squashed into a tiny pinprick. There were no dimensions. There was no length or width or height. And there was no fourth dimension of time, because time did not exist. During the Big Bang, space and time themselves were born. The radiation from the Big Bang expanded out in every direction. It was quite warm, 100,000 billion degrees. So hot that atoms and electrons couldn't exist. But just a tiny fraction after that inflation, everything started to cool down. And just 1 second after the Big Bang, the universe was 10 million kilometers across. And its temperature was practically cold. It was only 10 billion degrees. But it was cool enough so that electrons, protons, and neutrons had formed, these little particles that make up atoms. So how can we tell when the Big Bang happened? Well, what we can do is we can look at some of the first things that were made in the Big Bang, which were the galaxies. Now we know that the universe is still expanding today. And what I've got here is a balloon which represents the galaxies expanding. These black dots are the galaxies. And as it expands, so I can have a bit more expansion, as it expands, the galaxies start moving apart. And so we can see that the amount that it's expanded, okay, that's enough expansion, the amount that it's expanded determines the age and the size of the universe. And the oldest parts of the universe are the galaxies that are furthest away. To measure the age then, we can wind back time and look to see when the galaxies are touching. So let's run our Big Bang movie backwards. You can see all the galaxies coming back into each other. So everything was moving away from everything else after the Big Bang. And we can calculate how long it was since all those galaxies were back together. But to know that, we've actually got to know how fast the galaxies were moving. And to do that, we need to look at how light travels. Now, light's one of these amazing things that travels quite fast. It's about 300,000 kilometers a second. And if you were driving a car to catch up with light, you'd have to go at 670 million miles an hour. So that's fairly fast. The distance that light travels in 1 year is 10 million kilometers. And we call this distance a light year. And we measure lengths, distances in the universe in light years because the distances are so big, and it saves us talking about millions and millions of kilometers. We also think of light perhaps as just being white light. But we can see here, we've got some light shining through a prism. And it's split up into all the colours of the rainbow. It goes from blue at one end to red at the other. The blue is the short wavelength end, and the red is the long wavelength. I'm going to demonstrate this with a slinky. Could you just hold this end for me a minute, please? Thank you. As I pull, if we think of light as a wavelength, as I pull this out, the wavelength gets longer. It's red-shifted. It goes to the red end of the spectrum, and it's red-shifted. If I come back in again, the wavelength gets shorter. It goes to the blue end of the spectrum. It's blue-shifted. Thank you very much. We can see the same effect using sound. And for this, I'm going to put my hat on, and you'll see why in a minute. And I think it might be a good idea if you put your hats on.
Warning, effect imminent. Warning, effect imminent.
Right. Okay, are you ready for this? What we're going to do is we're going to listen to the sound of this alarm clock as I whirl it round. Now, I hope you can hear that as the clock comes towards you, the sound gets higher, and as it moves away from you, the sound gets lower. This is known as the Doppler effect. Okay, you can take your hats and glasses off now. You can see why I wanted to use the hard hat, don't you? Yeah. Okay, now let's imagine we're looking at light from a very old galaxy. Here's a light from a very old galaxy. Looks reddish in colour. That's because the galaxy is moving away from us. It's red-shifted. And the amount it's red-shifted is a measure of the speed at which it's moving away from us. And the further away a galaxy is, the faster it is moving away. We can measure the redshifts of hundreds of galaxies, like in this picture up here. The first survey of galaxies was done by astronomers going 1, 2, 3, 4, 5, 6, just counting like that. You can imagine, A, what a dull task it was, and B, difficult, keeping loose track. But the most recent survey was done by detectors on a telescope in Australia. This rather strange picture up here is real data. This is not a simulation, it's real data showing the positions that have been plotted of 250,000 galaxies. You see they make strings, there are holes where there are no galaxies. So this is what this part of the universe looks like. The furthest galaxies at the edge of that plot are about 3.6 billion light years away. So what that means is that when the light left those galaxies, there was only a primitive life swimming in Earth's oceans. Another way of measuring the age of the universe is to look for the remains of the radiation left over from the Big Bang, listening to the echoes. So I'm afraid we've got another life-threatening explosion coming up. So please put on your safety glasses.
Warning.
And your fingers in your ears.
Warning. Effect imminent.
Are we ready? 3, 2, 1. Bang! Whoa! Okay, we can see the evidence left. Okay, you can take your hats off now and your glasses. We can see the evidence left behind this Big Bang from the sand that's everywhere. But the Big Bang that started the universe left an echo and ripples in the background radiation. Those ripples went on to become galaxies and clusters. So let's hear how we can detect the echo of the Big Bang. The first measurements were made about 40 years ago using things like this. These are called horn antennae. And what they do is they listen. They're like great big ear trumpets. They listen for sound. More recently, satellites in space have been exploring this background sound. And they found that the universe is not totally smooth. This picture up here has patches of green and blue where these ripples are moving out, where there are clumps of extra matter. So when we look at the speed of galaxies, and when we look at the ripples in the radiation, we can learn about the age of the universe. We can learn the universe is about 13.7 billion, so that's 13.7 thousand million years old. That is when the Big Bang happened. There are billions and billions and billions of galaxies in the universe. They formed about 2 billion years after the Big Bang. First of all, from small ripples that formed tiny knots, then became great big clouds of gas. The more dense clouds built up. They merged and collided, and eventually galaxy-sized clusters were there. Galaxies don't live by themselves, though. They often form clusters of galaxies. Our galaxy is called the Milky Way, and it's part of the local group of galaxies. The nearest galaxy to us within the local group is called the Andromeda Galaxy, which is 2.5 million light years away from us. So it's a close neighbour, but when the light left that galaxy, Homo habilis, our ancestors, were roaming over the surface of the Earth. And our local group is not by itself. It's part of a bigger cluster called the Virgo cluster, which itself is part of a bigger group called the Great Attractor. So we're part of everything, and everything's moving around. Everything is in motion. The Earth moves around the Sun moves round in the Milky Way moves in the local group moves in the Virgo cluster, and the Virgo cluster moves to the Great Attractor. Everything is moving round at a speed of about 3 million miles an hour. Now that sounds like a huge lot, and we can't feel that we're moving at 3 million miles an hour, but that's because everything's moving as well. In a moment, we'll take a trip through some of the most stunning galaxies that have formed out of all this chaos. If we could fly through the universe, we would see thousands and thousands of galaxies. That's the bright bits, floating in the emptiness of space, the black bits all around them. What are these galaxies made of? Well, they're made of stuff that we can understand. They're mostly made of hydrogen, a gas made of atoms, molecules. The hydrogen atom is only 500 millionths of a millimeter across, so it's very small. But even though it's very small and tiny, we can understand it, we can predict what it's going to do. But you might be surprised to learn that actually only 3% of total matter is made up of stuff. When I was writing these lectures, the first thing I demanded was a large chocolate cake. Now this sliver is about 3%, all right? So that's only a very, very small amount. In fact, I haven't managed to cut it thin enough. So what's all the rest of the stuff? Well, about another quarter of it is something that's called dark matter. And dark matter is fairly mysterious. But the rest of it, which is about 70% of the universe, is made up of something called dark energy. And we know so little about dark energy. We don't know what it's made from, we don't know what its particles are, how big they are, we don't know how to detect it, that I'm actually not going to talk about it anymore at all. And I'm going to leave dark energy to you, the next generation of scientists, to discover what dark energy is. I'm going to talk now about this bit, the dark matter. What is dark matter? And why is it called dark? Does it matter? Well, actually it does. It's called dark because we can't see it, but we know it's there, and we know it's very, very heavy. That's how we know it's there. The reason it's there is when we look at clusters of galaxies. The way these clusters of galaxies move suggests that there's actually more stuff there than we can add up when you count and look and see how much gas and dust there is in those clusters. Actually, those galaxy clusters weigh about 10 times more. They've got to have about 10 times more stuff in them, more matter in them, than we can say there is there from the gas and dust. So there's a missing mass in all the galaxies. And the missing mass is about 10 times as much as there is of the real stuff. And we call this missing mass dark matter. So about a quarter of all the universe is dark matter. So what makes up this dark matter? Well, we think it's made up of some strange particles called WIMPs. A WIMP is a weakly interacting massive particle. Massive particle. It weighs a lot. Weakly interacting. It doesn't do much. It doesn't interact with us. That's why they're impossible to spot. And they actually are just about impossible to find. However, rumour has it that parts of the missing universe can be found in this small North Yorkshire village of Bulby. Every day, hundreds of thousands of millions of particles are streaming through my body. Some of these are cosmic rays that come from space, but others are WIMPs. But only 100 or so of those actually interact with the atoms in my body. This makes them extremely difficult to detect. Some ways needed of filtering out the WIMPs from all the other stuff. Down there is a place which helps scientists do just that. Over a kilometre beneath my feet, a team of scientists has spent 10 years looking for these elusive WIMPs. If we're going to have any success in finding any today, I think we're going to need some help. Is home to one of Europe's deepest mine shafts. The journey to the bottom takes 8 minutes and is a frightening ride. It's so windy, you really have to shout to make yourself heard. It feels just cold and drafty and very, very noisy and rattly and shaky. It's really dark, you can't actually see where you're going or anything.
It's getting really cold, yeah. It's really daunting actually, going down here.
My ears have just popped a couple of times and I can't hear properly at the moment. So we're about halfway down now, about 500 metres down below the Earth's surface. So we've got this 500 metres of solid rock over us. And that means we've blocked out most of the cosmic rays and the high energy stuff that can really punch their way through the atmosphere and rocks, and so most of that is blocked out. So
Stop.
we're here.
Hidden amongst a warren of dusty caverns and tunnels is a specially constructed clean lab. It houses a machine built there to detect WIMPs. Jamie Dawson is one of the scientists who works on the project.
We are searching for an extra component to the universe that we're pretty convinced through lots of experiments and observational work doesn't make up what you and I are made of. So we're looking for a particle, but it's completely alien to us. It's not like light, it's not like protons and neutrons in your body. It's a new type of subatomic particle.
So what is this then?
This is drift.
The chamber is filled with carbon disulfide gas. Should a WIMP enter the chamber, it will collide with an atom of the gas. The resulting impact will be measured by these fine sensor wires. If an impact is recorded, it will prove that WIMPs do really exist.
So have you actually found any WIMPs yet?
No, we haven't. I mean, at the moment, the kind of masses that we're operating, we're pursuing a technology to detect something, but we don't quite anticipate detecting something with this detector.
To increase their chances of capturing WIMPs, Jamie and the team hope to build a bigger and more sensitive tank. Only then will the mystery of dark matter be solved.
So even though we don't understand dark matter, we've got a lot of experiments going to help us try and understand. But we can actually still study the galaxies that are embedded in that dark matter. The galaxies speeding away from us. Some of the most stunning images of the galaxies have been taken by the Hubble Space Telescope. In this picture, we can see millions of galaxies. If we can imagine flying through it, we'd see galaxies of different shapes, different sizes, different colours. We'd pass galaxies with strange shapes. There'd be whirlpools. There'd be Catherine wheels, sombreros, and spirals. Seems like a dazzling variety of shapes and sizes, but actually when you get down to it and you look at them, they divide into two types, the ellipticals and the spirals. Now the elliptical galaxies, well, to be honest, they're a bit not very spectacular to look at. They're just like smudges. And even though there are 4 times as many ellipticals as spirals, they don't take a good picture. They're made of old stars. There's not much gas or dust. There's not really very much going on in old elliptical galaxies. But spiral galaxies are much more interesting. A spiral galaxy has a central bulge of old stars, and it's got these long arms which swirl out containing new stars and gas and dust, and this is where new stars are made. Now, galaxies aren't just static. They merge and they collide. Like in this picture here, you can see 2 galaxies merging and colliding, tearing stars, gas and dust away from them. One galaxy is being eaten up. Galaxies aren't safe places. There are monsters that lurk in the center of those galaxies. The monsters that lurk in the center of a galaxy is a black hole. This is a graphical representation of a black hole. What is a black hole? Why is it black? What's at the bottom of it? What's at the other side? What would happen if you fell through one? No one's ever seen a black hole. We only know about them because of the weird effects that they have on other bodies that have veered perilously close towards them. So how can we explore what black holes are if we can't see them, if we can't take a photograph of them, if we can't look at them? These dancers are showing us about black holes. You can't see the dancer in black, but you know that there is something there because the dancer in white is spinning round. So this is like a black hole with stars spinning round it. It's the same as stars revolve around black holes. Thank you. So here we can see a black hole feeding on a star, sucking it in. Black holes absorb all light. That's why they're black. They reflect none of it back. And we think of black holes as being massive, and they are. They are absolutely massive. That is, they're full of mass. But they're not big. The black hole at the center of our Milky Way is only about 15 million kilometers across. Now that's a tenth of the distance between the Earth and the Sun. So that's not very big at all. But the black hole in the center weighs about 3.5 million times that of our Sun. And there's also thought to be thousands and thousands of very tiny black holes, only a few millimeters across. And these were made in the Big Bang out of the radiation that was expanding outwards. And these float through the universe. There might even be some in here, who knows? Black holes aren't all the same. Some rotate, some are stationary. And I'll come back to that in a minute. So let's see how a black hole can be represented. This sheet here, it might look just like a rubber sheet to you, but to me, this is the fabric of space and time, and I'm going to curve it. All right? So this big ball, this deep well, is what happens with a black hole. It bends space and time, and so things fall in to the black hole. They fall in towards the center, they get sucked in, and they don't fall out again. So a black hole is a region of space where mass is concentrated. And we think that some of the missing mass, some of the dark matter, actually might be locked up in black holes. Now, strange things happen to things when you get too close to a black hole. So what do you think would happen to me if I were to veer too close to one? Well, here I am, falling close to a black hole. All right? Now, what you would see is that I would be spaghettified. I would be stretched because time, it would seem to you as if time was standing still, and I would get longer and longer and longer. That's called spaghettification. Thank you. Okay, and so as I went down the black hole, I'd be crushed to zero volume at the center of the black hole, the singularity. Now, to explore more about black holes, I need my men in black to help me. So, stationary black holes have this thing in the center of them called a singularity. And if you fall into a singularity, that's it, you're a goner. But some black holes rotate, and then you might, as you fall through the rotating black hole, you might miss the singularity, and then you'd be falling down a wormhole. Okay, Ben, come down and show us what it's like when you go through a wormhole. If you crawl through this tunnel through space and time, you might go in one end on a Thursday in 2003 and come out the other end in the future in a completely different region of the universe. Wave your flag. We could use wormholes to leap between distant galaxies. So we'll explore these ideas of wormholes and time travel later in our voyage. I know it sounds a bit like science fiction, but serious scientists actually are starting to think about wormholes and time travel. And I'm rather hoping that sometime in the future, you, somebody from here, will be able to understand and discover about time travel. And what I hope you'll do is in the future, you'll come back to me here and now and tell me all about it. We've looked at some of the monstrous atrocities that lurk inside our galaxies, but we haven't yet really explored the violent and beautiful things in our galaxies. What we're going to look at next is the birth and death of life-giving stars. If you were to travel for a long time through the depths of space, occasionally you would see a bright flash like that, an exploding star, a supernova. These are powerful explosions when a star dies and returns its ashes back into space. The star is recycled. This is a picture of a star cradle where new stars are being born. Stars are born, they evolve, they die. Star formation is a cyclical process. Stars come in an array of sizes, colours and temperatures. And the different colours tell us different things about the different types of stars. So, yellow light maestro, please. Thank you. This yellow light here represents the sun. That's the size of the sun. As the sun grows older, it turns into a red giant. It expands, would fill the size of the lecture theatre. And then as it continued to grow older, it would become a white dwarf, this size, and would then gradually fade away. This is a simulation of stars being born and dying, stars being made in one turbulent cloud of gas and dust. The gas and dust is churned around at unimaginable speed. Star formation is going on today in the Orion Nebula. As stars form in the gas clouds, the gas spins faster and faster and faster. Now, as something spins faster, it gets smaller, it contracts. So the roller skater here, who is spinning faster, represents the matter which is spinning fast and fast enough so that the gas will start to fuse. So the star is now switched on and starts to shine. Thank you. Stars are a factory where chemical elements are born. We're going to explore this by using young school students to act as chemical elements. Here, the red t-shirts are molecules of hydrogen running round in an ordinary star. They collide, make an atom of helium in the blue. Eventually, all the hydrogen becomes helium. And the helium, the star is now a red giant, and the helium atoms run around and eventually will collide. They become carbon, a group of 12 mass units. And this is what happens with stars. The chemical elements build up and up and up until you get to iron, 56 units. 2 iron nuclei cannot fuse. There just isn't enough energy in the system. The star collapses and explodes suddenly, rapidly, as a supernova, giving out vast amounts of energy. And in this vast amount of energy, you get heavier elements formed, like gold, uranium, and lead. All the elements in the periodic table are made in stars. So you, the chairs you're sitting on, me, we're all made from stardust. Let's look at our own star, the sun. Our star was formed about 4,567 million years ago out of a cloud of gas and dust that was rotating and turbulent. You can see the picture here. It might look a bit like a UFO, but what this is a new star forming with a disk of dust all the way around it. We should try and investigate what's going on inside the dark cloud. As the cloud spins round, gas and dust spiral inwards. The middle of the cloud gets extremely hot as the gas starts to compact. This could be our star, the sun. This is how it formed. But what happens to the stuff that's left over? This candy floss machine perhaps could give us some sort of clue. I've got a jug here of sugar. But let's pretend it's not a jug of sugar, but it's actually a jug of solar system dust. This is the stuff that was making the planets. How can we turn the solar system dust into the planets? Spinning round, the leftover dust and gas started to clump together, dragged in, forming rocky planets. The candy floss machine shows what happens. As the dust spins round, it starts to clump together, making bigger and bigger and bigger clumps, and bigger and bigger and bigger clumps. Now here, I'm using a big stick to collect up the candy floss, which I'm now going to switch off because I've got enough planets. So what I was doing was collecting up the dust into a clump. Now, obviously, the solar system wasn't made in a big candy floss machine, so it wasn't a completely realistic demonstration. For a start, there wasn't a big stick in the protoplanetary disk. It was gravitational attraction that pulled all the bits together. The dust fell inwards to make the rocky planets. Jupiter and Saturn accumulated from the gas and dust that wasn't dragged inwards. And then further out, where the temperature was much colder and water could condense as ice, Uranus and Neptune, the ice giants, were built up from the ice and gas that was remaining. Now this whole process took place very, very quickly. Only 1 to 2 million years. Now that might sound a long time, but when you think that the whole age of the solar system is 4,567 million years, it only took 1 to 2 million years for this planet-forming process to happen. After that, over the next 30 or 50 million years or so, the planets got compacted, got hot in the middle, cores started to form, and they started to look like the planets that we know today. 9 planets were formed. Our Earth is the third rock out from the sun. The planet one further out from us looks something like this. surface is red, rocky and windswept. For the next leg of our voyage, we'll be setting foot onto the surface of the red planet Mars. In a special show tomorrow at 12, we'll be live and interactive with special guests in the studio. With their help, we'll be exploring Mars's extreme geology, flying through its stunning canyons and exploring the highest mountain in the solar system. We'll investigate if its mysterious terrain might once have harboured life. We'll be challenging you to build and land your own craft on its surface and see how space engineers do it for real. We'll speculate how we might one day set about transforming Mars into a planet fit for human habitation and explore the challenges that await the daring individuals hoping to be the first humans to leave their footprint on its surface. So if there was, or still is, life on Mars, I want you to fax me a picture of what you think it might have looked like. What would you say to a Martian? Text and let us know. And you can email your comments and questions for me and for guests who will be appearing live throughout the show at mars@channel4.com. So join us tomorrow as we unearth the mysteries of the red planet.
And that's at 12:05. To order Voyage in Space and Time, the booklet accompanying the lectures for $5.99, call our credit card order line on 0870 400 2240, or to find details of the postal address and how to build your own alien game, log on to channel4.com, RI Lectures 2003. Next, it's the 100 Greatest Musicals.